Okay. So as we indicated in the beginning of class today, this is the part of the outline we're working on. So I want to share with you some fundamentals of what is called the common ion effect and how the common ion effect is used to prepare buffer solutions, and then we're going to go through calculations associated with predicting the position of pH as you titrate, say, a strong base into an acid. So, the first topic is the common ion effect. When an acid or a base or salt ionizes, it delivers into solution a cation and an anion. These are referred to as common ions of a given solution. For example, if I have a solution of acetic acid, it's going to have hydronium ions and acetate ions in it. Now, let's say you come along and pour into this solution, solution 2, a solution 2 having a common ion. That means one of or the other of these ions, say HCl solution. Like that. Well, what you're doing is you're adding a common ion of that solution you're pouring the acid into. Or you might have a system that contains, say, sodium acetate, or HOAC, like that, and from the outside maybe add a sodium acetate from outside that ionizes the sodium plus the acetate ion. Well, the acetate ion is a common ion to ions already in solution. So this is what the idea or concept of common ion means, is that you're pouring some common ion solution into a weak acid or weak base solution that already has some ions in it. Well, this also applies to addition of ions of a salt that's undergoing ionization too. We'll see in the next chapter. Well, what happens when you add a common ion to a solution of weak acid or weak base is the effect of adding common ion is to reduce extent of reaction. So what we're saying is we're going to calculate the percent ionization, for example, of acetic acid in pure water, and compare that with the percent ionization if we have that acetic acid in a solution with a mixed solute, or a common ion, either H or OAC. And we'll find out that the ionization of pure water is much greater than the percent ionization in common ion, or with common ion. So we have what was referred to in the community normal extent of reaction, or normal ionization, and then you have reduced ionization due to the common ion effect. So a problem that we want to pose to you is as follows. First, let's calculate percent ionization of a 0.10 molar acetic acid. And Ka is, I'll just use 1.8 times 10 to the minus 5, okay? And then to calculate percent ionization of 0.10 molar acetic acid with 0.01 molar, we can call it sodium acetate. Well, you're only really interested in the acetate ion, and the sodium is not a common ion to the HOAC. So we call it normal ionization, that is in pure water. You do not have any common ions. So if we had given a 0.10 molar acetic acid and Ka equals 1.8 times 10 to the minus 5, then we know the hydronium ion will come out of that 0.1 molar, right? Let me do it. Put this down. HOAC, it will go to, of course, hydrogen and the acetate. So how much hydrogen will come out as compared to the amount you started with over here with HOAC? We're starting with 0.1, so how much hydrogen will be generated? Well, the ratio times 100% will give you the percent ionization of the acetic acid under those conditions. Okay, so we want to calculate the hydronium ion. Since it's a weak acid, we use the square root formula. Mole per liter. I believe that's 0.0013 molar in H plus ions. On unfreezing. Let's see if it does. Check it. Yeah, how about that? Okay, so the percent ionization now of the HOAC is the amount of hydronium ion generated in the ionization divided by what we started with. That's the part over total times 100%. So that is a 0.0013 divided by 0.10 times 100%, and that comes out about 1.3% ionized. Right there. So now we want to compare this process in the pure water with something that has one of the ions already present, and we should get a number less than that value. So I'll move this up here, and we'll keep it visible as we go through. So now we want to calculate percent ionization of 0.10 molar acetic acid in a 0.01 molar, we'll take, what did I say, sodium acetate a while ago. Sodium acetate is what you will deliver the common ion in, but we're not interested in sodium because it's not a common ion. Now, in calculating this, you have to use the ice table. In the pure water ionization, we were able to go straight to the hydrogen by the square root formula. But in common ion calculations, do not use the square root formula. I'll say it again. The common ion calculations do not use square root. You have to use the ice table. So the ice table is based upon ionization, of course, of the weak acid that we're working with. And Ci changing C and C at equilibrium. Now the issue is, in common ions, this is already present in addition to the weak acid. That is, in the initial row, we have 0.10 molar in the acid and 0.01 molar in the acetate. And we assume those are in the starting gate, so to speak. And nothing's happened yet. That is, in the presence of the common ion, HVAC hasn't started delivering hydrogens into solution yet. Then you open the gate and let the chemicals run. The reaction run, and so this goes down by X, and plus X. So this is why you have to use the ice table. You don't have equal amounts here. One has a significantly higher concentration than the other common ion. Now, this problem can be worked against given hydrogen and an unknown acetate to get the percent ionization also. But anyway, this is a 0.10 minus X, and 0.01 plus X. And you can drop the X here in 0.01 molar and 0.10 molar. So this is what you apply to the Ka expression. And so from our reaction, we have HOAC divided by HOAC. And then this, we put in the equilibrium concentrations, 0.01 divided by 0.10. Everything comes out in moles per liter at the end of this. So, and the Ka value is 1.8 times 10 to the minus 5. So we want to solve this expression for X. And so X, which is equal to the equilibrium concentration of your hydrogen now in the presence of the common ion, is equal to 1.8 times 10 to the minus 5 times 0.10 divided by 0.01. Comes out in moles per liter. And just to be sure, I'm not assuming anything, and so this gives me a 1.8 times 10 to the minus 4 molar in hydronium ions. Remember, in pure water, the ionization gave 0.0012 molar in hydronium ions. But now we're at 1.8 times 10 to the minus 8 molar in hydronium ions, a significant drop because of the presence of that common ion. And when we calculate the percent ionization, we can use the hydrogen again over the OAC times 100%, and so that is 1.8 times 10 to the minus 4 divided by 0.10 times 100%, 0.018. 10 to the minus 4. Yeah. 0.18% ionized. Ionized in common ion. Right here. And we remember in pure water, this gives us a 1.2% ionization. So in pure water versus the common ion, there's a significant decrease in the amount of or extent of reactions, what I'm trying to tell you. And so that in essence is the common ion effect. Is buffer solutions. A buffer solution functions to limit, not prevent, but limit changes in pH when large quantities, reasonably large quantities of acid, strong acid or strong base or hydronium or hydroxide are added into that buffer solution. So this is the nature of a buffer solution. Buffer solutions function to limit, not prevent, changes in pH when quantities of hydronium ion acid or hydroxide base is added into buffer solution. From an instructional point of view, I want to show you three things. Okay. One, well, how to calculate the pH of a buffer solution. Two, comparison or pH of solution after buffer solution after adding an acid or after adding a base. Like that. Really is. And showing you also how to calculate the same things, but we'll be using solution data. So as we go along, you'll try to keep these 3 points in mind, because these are the objectives of what I'm trying to teach you in working with buffer solutions. Okay? Well, certainly we want to begin with calculation of pH of buffer solution. Well, without question, how do we calculate pH anyway? It's the minus log of the hydronium ion concentration. Like that. So, given a buffer solution, we want to focus on the amount of hydronium ion. Now, buffer solutions come in acidic, neutral, or basic. I should have mentioned this before. Buffer solutions types, or buffer solution composition, is a weak electrolyte plus the salt of weak electrolyte, which provides the common ion. Now, the weak electrolyte can be a weak acid or a weak base, but in preparing the buffer, you also want to include that conjugate acid or conjugate base of the weak electrolyte. So what we're going to start with is a 0.10 molar acetic acid plus a 0.10 molar sodium acetate mix. And this being the weak acid or weak electrolyte and the salt of the weak electrolyte. Right there. Now, all of the calculations are based upon the ionization of the acid. Keep that in mind. The salt provides the common ion in the Ci row of the ice table. So for the buffer mix, we have HOAC, hydronium ion, plus the OAC. And what we're ultimately looking for is this hydronium ion concentration and the minus log of that number, based on these numbers up here. So it's Ci, change in C, and C at equilibrium, and I'll move this up now, is 0.10 molar, 0, and 0.10 molar. And then the equilibrium is established, decreasing by X plus X and plus X, giving 0.10 minus X molar, X, 0.10 plus X molar. And we can drop the X, 0.10 molar, 0.10 molar. I haven't done anything you haven't seen before. This, in essence, is called a 50-50 buffer, which simply means that it has equal amounts of weak electrolyte and common ion in the concentrations. Well, that provides us with a unique outcome when we calculate the pH values in hydrogen concentration, because this is added into, the concentrations are added into the Ka expression, and you remember the Ka expression is products over reactants, just like we've always used. And you can see how the substitutions, we have the hydronium ion concentration of X times 0.10 divided by 0.10 molars, and those two will drop out, and X in a 50-50 buffer always equal the Ka value, or X being OHs in a weak base would be a Kb value. So in a 50-50 buffer, the hydronium ion concentration is equal to the Ka value. Or in a 50-50 weak base conjugate acid solution, it'd be equal to Kb value. Well, that's that. Here we go. So you could take this table and if you wanted to make an acetic acid buffer, acetic acid acetate buffer, 50-50 between the acetate and the acid, that would be your hydronium ion concentration. All you'd have to do is take minus log of that number. Or if you want to make a buffer using benzoic acid, you take a 50-50 mix of benzoic acid and the benzoate, sodium benzoate, potassium benzoate, the conjugate base. And that is the hydronium ion concentration. Just punch in minus log of this number. So any of these that you want to use in making that buffer system, all you got to do is take the minus log of any of those Ka values, and you'll get the pH of that buffer solution. So in the case of the acetic acid, the Ka value, if you saw it, was 1.8 times 10 to the minus 5, and from the tables. Therefore, if Ka equals the hydronium ion concentration, then the pH is equal to minus log of the Ka value. And so we can say that pH in this case is minus log of 1.8 times 10 to the minus 5. That gives me a 4.75. So this is your initial mix of the buffer solution. So the idea here is, here we have this HOAC, 50-50 HOAC, all right, 50, a 50-50 HOAC, OAC minus buffer. And it has a pH equal to 4.75. Now the question is, and the use of a buffer is, if you add excess hydronium ions from an acid or excess hydroxide ions from a base, what happens to that pH? That's what I want to show you now. So in general, so you can watch for this as it's coming up in the calculation. Addition of H plus acid decreases buffer pH. That's a generalization. Addition of hydroxides from a base will increase pH. So as we go through the calculations that I'm about to do for you, watch for these trends in the effect of adding acid or base to the system. Okay, now we're going to use this 50-50 buffer, and we're going to say the acetic acid and the OAC are in the system at 0.1, just like we calculated originally. So in the effect of change, you still use the same ice table and the same ionization. So HOAC goes to H plus OAC minus. Put down your CI, change in C, and C at equilibrium. So look back and on how we prepared it in that ice table in the initial preparation, calculation of pH. It's the same here. We start out with 0.10 molar and 0.10 molar. Now, of course, this buffer solution has a hydronium ion 1.8 times 10 to the minus 5 molar here. That's a real given because Ka equals the hydrogen in this particular buffer. However, what we're trying to calculate is the new, I went too far, the new hydronium ion concentration after adding the acid or base that we're going to put in here. That's the big question in this, and how does that affect? So if we're just simply looking for a new one, then we're going to assume H plus in such a calculation equals 0. So this is just going to turn into a 0 right now. And then we're going to set up and do the changes. Okay, so what we're going to do is for this problem, we'll start with acid. So calculate pH after adding 0.02 molar in HCl, which of course gives you 0.02 molar in excess hydronium ions, right? So you have your buffer solution, which is the H plus and HOAC, and then your OAC in solution here. And then what you're doing is you're throwing in some HCl. Well, of course, the hydronium ion is your common ion that's going to affect this system. So does everybody kind of understand the problem? That's real important at this point. Anybody? So we're taking that equilibrium and we're throwing some HCl on it. Or we could throw some sodium hydroxide on it, right? To analyze this, use the sea salt. Okay, so what we're going to do is we're going to take our buffer and put it on the sea salt, like this. And then we're going to add H plus. Put it this way. Add 0.02 molar in HCl, which is the same thing as 0.02 molar H plus. So if you add H plus to that sea salt, which way will it tilt? It'll tilt right or left? Right. So you're loading up here, right? On your seesaw, so adding will cause the seesaw to tilt to the right. Now, this is not an equilibrium. This is what breaks the equilibrium when you put that extra acid in. Now, the tilt, the reaction now shifts away, Le Chatelier's principle, shifts away from the addition, which is the extra acid, to reestablish a new equilibrium. So the reaction is going to shift left. The buffer solution shifts left and creates the new equilibrium with new HOACH and OAC concentrations. So everything is changed in our equilibrium. How are we doing? Following me? Okay. So what does that mean in terms of the calculation? How do we get this new hydronium ion concentration and take the minus log of it? Well, again, you still have to use the ice table, but what happens right here in the shift in terms of the concentrations of the acetate and the concentration of the acetic acid in order to get the new balance? It's shifting left, right? Right to left. So what does that mean? That means the OAC has to go down by combining with H. Yes? See that? Please, see that? If you don't, I'm just wasting my time. So if this is tilted to the right and shifts left to reestablish a balance, OAC is going down, and this has to go up. HOAC has to go up. Yes? By how much? By the amount of HCl you put in, because the buffer solution chemistry has to remove the excess. Okay, so this is what you need to look at. HOAC in equilibrium with H plus the OAC, CI change in C, and C at equilibrium. So you start out with this, say hypothetically 0, and 0.10 molar in this. The change in concentrations, what did you just say? This decreases, this goes down, and this one has to go up. So if the OAC has to go down, we want to subtract the 0.5 molar from the OAC that we started with, because it's shifting left. And over here, we want to add the 0.5 molar right here because it's going up. See that? Yes.
Where did you get the 0.5 molar from?
Did I give that back in the beginning of the problem? Somewhere right, maybe, 0.02, sorry. I don't know why I changed it to 5. Senior moment. Thank you, sir. That should have been the 2, thank you. So we're increasing or decreasing, get rid of that 0.02, thank you, sir. So when you add these two together, what's the equilibrium? And so you do the new calculation for hydrogen, which is your unknown right here, based on these concentrations, which is 0.08 molar now, and this one goes up to 0.12 molar. See how those changes took place? And so that's why I say all we're looking for is how this changes, going from 0 to here. That's why this disappears instantly anyway. Okay, so you apply new concentration values to the Ka expression. And as a result, you have the new hydronium ion concentration. So Ka is still hydronium products over reactants over HOAC. And then we put the equilibrium row in. 1.8 times 10 to the minus 5 gives us the new hydrogen times 0.08 divided by 0.12, and then solving for hydronium ions, we get 1.8 times 10 to the minus 5 times 0.12 over 0.08. And if I didn't make any mistakes now, we can calculate the new hydronium and, of course, the pH after adding the acid. And so I get 2.7 times 10 to the minus 5 molar in H plus nu. Right there, and of course this gives me a pH minus log hydrogen. And minus times a minus a plus, so this will reduce to 4.56. Now we started with 4.74 pH at start of the 50-50 buffer was 4.74 or 5. pH after adding H plus from the HCl, we go to 4.56, more acidic pH. So adding acid reduces the pH values. Now I want to do the same thing with addition of sodium hydroxide or a strong base, whatever that involves. Consider that you're given a 50-50 buffer with those concentrations, and we're going to add a 0.05 molar in the sodium hydroxide this time. And again, we take into consideration, well, what's happening and how does this shift? And so one of the things you have to understand is when you put the sodium hydroxide into an acidic buffer, what you have, and this is this is all you have right here, the hydronium ion, the acetate ion, and this. So if you put this on a seesaw, how is the addition of hydroxide to that equilibrium affect the tilt, if you will, of the seesaw? Well, what it is this hydroxide will react with the hydroxide and form water. That's the way this affects that tilt. And essentially what you've done is, in the equilibrium for a moment, is you've removed the hydronium ion by the presence of that hydroxide, and so for initially you have this. And so, since it looks like somebody got off of the seesaw, then the results is to tilt left like this and shift to the right to replace the hydronium ion. And it'll continue to do that until all of the OH is removed. And so you see how the chemistry of the buffer functions to push that excess out of the system. And so then the concentration, in order to shift to the right, the OAC concentration decreases, and the OAC increases. So that's how we set up the ice table. We start out with the original balance and then add and subtract to the left or right based upon how that shift occurs. Everybody kind of follow that? Okay. So if it's going to shift to the right, then I would have to subtract from the concentration over here and then add to the concentration over here the amount of OH that was added into the system, and it's of course a 0.05 molar. So we'll take that idea and set up our ice table. And so the original buffer solution, 0.10 molar, and we'll just assume that's 0 because that's what we're looking for, and it's 0.10 molar. And so we want to apply this shift because the hydronium ions are being taken out by reacting with OH going to H2O. And so if this is going to shift to the right, then we have to decrease in the change over here on the acetic acid. So this is negative 0.05 molar, and this time the OAC increases 0.05 molar, and or O2. I keep using O5. I'm sorry. O2. And so at equilibrium, the new equilibrium will be a 0.08 molar and a 0.12 molar this time, and the new X is the new hydronium ion concentration. So everybody okay so far? And what's happening? Any questions? Okay, so this applies to the Ka expression, H, we see, and that's 1.8 times 10 to the minus 5, X, which is our hydronium, 0.12 over 0.08, and that's 1.8. And so solving for X, which will be our new hydronium ion concentration, 0.08 times 1.8 times 10 to the minus 5 divided by 0.12, and all that's in moles per liter. And so we'll see what the new hydronium ion concentrations are in this case. So we now have a 1.2 times 10 to the minus 5 molar concentration of the hydronium ion. To start, remember, with 1.8 times 10 to the minus 5 molar in hydronium ion concentrations. And so we went from 1.8 to 1.2. So as you remove the hydronium, which is removing acid, what's the change? It's basic. So since you're removing acid, you have to be going in the opposite direction, which is into the base. So if that's our new hydrogen, the pH, I put new, is minus log of hydrogen that takes us to 4.92 after adding NaOH. And so, just to summarize this, the pH acid after HCl, remember, what was that number? 4.7, 4.6?
4.56.
Thank you. 4.56, and then pH of the 50/50 buffer before adding anything was 4.75, and then pH after NaOH was the 4.92. So we have increasing pH for OH added, and then we have a decreasing pH for H plus addition. And this one is a 50/50 buffer. Now, understand here that I've kind of padded the bill, so to speak, with the 50/50 buffer so that the Ka equals the hydronium ion concentration. But a buffer pH depends fundamentally on the conjugate base acid concentration ratio, because you don't always make your buffer with a 50/50 system. That's just a convenience, and it exists. And some people will make them that way for, instructional purposes or whatever. But in some research circumstances, you don't have that. But in a more practical environment, pH of buffer systems depend upon concentration of weak electrolyte and salt of weak electrolyte. Like that. And so we can make a pH at any position we want. So if you need a pH, say we did a 50/50 HOAC, NaOAC, and came out 4.75. Okay? What if you needed a 5 pH in an acetic acid OAC? Assume need is a HOAC OAC minus buffer with pH equal to 5.00. Just made it up. 5.50, whatever you want to choose. Well, how do you deal with that? Well, there is a way to calculate the base acid ratio when you are preparing your solutions. And it's done by using a thing called the Henderson-Hasselbalch equation. I have to look this up every time I JSSEL. this equation is derived from the general Ka expression for a weak acid, assuming the A is an anion over HA. It can be shown that the pH of a buffer solution is equal to the pKa of the acid plus log of the base concentration, conjugate base, divided by the acid concentration. Now this applies also to determining the acid-base ratios in weak base and their conjugate acid combinations also. So if I'm preparing a 5 pH, then I will put in here for the pH, say you're given a pH equal 5, what is the acid-base ratio? Oh, also, or base to acid ratio. There's a problem where you have to take the reciprocal. Anyway, using this, and let's just do the, let's do the base to the acid ratio first, and then do the acid to base, base over acid ratio, and then do the acid. Base ratio, because that's the way the equation's written to begin with, like that. Okay, so what you do is you, of course, substitute your 5 into the pH. But what do you do for the pKa? And the only thing left is that ratio, log of the base over the acid. Okay? Now, I'll show you this part in a moment. But how do you pick your pKa? Now, pKa in this is the pKa of the acid, or pKb of a weak base. The rule is to pick a pKa value plus or minus 1 of the target pH you're trying to make. pKa equals, you're choosing choosing your acid, I'll show you. pKa should be pH needed plus or minus 1. Anything bigger or smaller than that just really skews your acid-base ratios. So what you have to do in this case is get a table of acid-base Ka values like in here and start taking minus logs of everything in here until you get out. And then there are tables online that have the Ka values and the pKa's right by them. And you just look up something that's close to the pH you need, plus or minus 1. Okay, so I don't have one in mind right off, but we'll. Call the Henderson-Hausbach the H equation. I think that's easy enough. Easier. Okay. And remembering pH equals pKa plus log, and it's always in this published form, in any text, it'll be the base over the acid. So most problems will ask you for base-acid ratio. But you also have those acid-base ratios. Given base over acid ratio. This ratio, what is the acid to base ratio? So you be careful when you read your problem. And of course, that's just simply the reciprocal. So the acid base ratio is 1 over the base acid ratio, which gives you that value. So if you solve your equation for the base over acid ratio and you get a number, whatever it is, just take the reciprocal of it. But what I'm telling you is when you're on test day, you want to be careful that how you read the buffer problem as you read through and work through your practice exam. You probably find that if you haven't already seen that. So that's the issue. So, okay. Okay, calculate pH buffer 25 milliliters of 0.15 molar ammonium hydroxide, which will be ammonia in the practical sense, mixed with 30 milliliters, 0.20 molar ammonium chloride. So you're working in an environment that is not in pure molar terms. And so you have to determine how the equilibrium NH4OH is affected when making your solution. And so this goes to NH4 plus OH minus. So in this, you're really looking to calculate your OH out of this combination. And once you get OH, you get POH and pH. So you have a couple of steps at the end of this that you didn't have in the acid and the molarity issue. Also, when you put terms into your ICE table, you have to put them in terms of molar concentrations, not solution concentrations like this. So all of this needs to be in molar terms. So we have to convert these to molar terms, moles per liter of the mix. Now notice your mix is a combination of 25 and 30. So when you calculate moles, and you remember moles is equal to molarity times volume in liters. Okay? And then molarity is moles, which you will calculate using this, divided by volume of mix. That's your solution mix in liters. Moles of solute, that's your weak acid, weak base in this case. Weak base, how much of that you have over the total solution. Or no, it is a solute because you're going to do the molarity of both of them, just weak base and your salt. I'll just take that out because it's both of them, really. Okay, so let's take this and set up. Try to keep it on page so I can see that. So what we're doing is we're taking an NH4OH in equilibrium with NH4 plus OH. Now don't forget this is a common ion problem, all of them. Because when you mix the conjugate with the acid or base, then you have a common ion problem. Now, so we'll start out by looking at let's just get the concentrations. Concentration of NH4OH, or I don't want to do it that way. Here, I'll do it this way. I got it. All right. Given this, 25 milliliters of 0.15 molar NH4OH plus 30 milliliters of 0.20 molar NH4 chloride. Okay, so there's your base and common ion. So now, I'll show you how to deal with this. This becomes moles if you go molarity times volume. Well, in liters, 0.025, move the decimal 3 places, times 0.15 is moles ammonium hydroxide plus 0.03 times 0.20 mole of the ammonium chloride. That's it. Making a mess. Now that looks better. So now multiply these together and you get the moles, but you remember you've got them in a mix of 25 plus 30 or 55 mils. And so let me punch that out. And that is 0038. And then you work that one. Times 0.2, 006 mole of the NH4. And I'll just leave it at that because that's your common ion. Chloride is just a spectator ion. Like that. Now, we get this to molarity, then we can apply it to the ice table, is what I'm trying to get to. So now we have 0.0038 mole over 0.055 liters. That is, you remember, is in 25 plus 30 is 55, and so moves the decimal 3 places to the left, and this is your buffer solution right down here, this 0.55 liters. The ammonium hydroxide. The same way with this one, 0.0060 over the 0.055 liters of the ammonium common ion. And then running that out, divided by 0.055. And so that's 0.11 over here molar in the common ion. I just happen to have the 6 in there. And 0.0038 divided by 0.055070. Okay, 0.07 molar in the weak base, the ammonium hydroxide. So this is what you apply to the ice table. But when you get solution data, you have to first get it in molar terms like this, and then NH4OH goes to NH4 plus OH minus, change it C, and then CEQ. And of course, when you finish this, you're going to have an OH number, which you have to translate into hydronium ions and pH. So here we're starting with 0.07 molar and 0.11 molar, and assume 0. And then this is going to go down by X plus X and plus X. And 0.07 minus X, which is 0.07 molar, X and 0.11 plus X, 0.11, molar, and then X. There we go. Is everybody okay so far? I mean, it's just a flow as you go through the solution data. So my biggest thing is trying to impress upon you how you, if you're given solution data, you're still going to do the same thing down here and get this X value from the equilibrium, but you have to first convert everything to molarity. Yes, Anthony?
Can you scroll up?
I'll be glad to. I certainly will.
Thank you.
Yes, sir. Okay. Anybody else anybody follow me? Now here you do the same thing as we did the other. Once you get your equilibrium row, your brain should say equilibrium expression. There's nowhere else to go because these are plugged into that equilibrium expression and solve for the X. And of course that's the OH in this one, and which will translate into hydronium and pH. So the equilibrium expression is a base for this, and so that is ammonium ions, hydroxide ions, NH4OH, and that's equal to 1.8 also times 10 to the minus 5. Yeah, I'm going to look it up if you want to. 1.8, and so the equilibrium rho for ammonium is 0.11 molar, and X divided by 0.07, and then we solve for X, which is your hydroxide concentration in the equilibrium, and that is 0.07, 1.8 times 10 to the minus 5, 0.11 molar. .07 times 1.8 times 10 to the minus 5 divided by 0.11 gives me 1.15. So you can either go through the minus log of that and get the POH and then subtract it from 14. So pH is 14 minus POH, which is 14 minus, I'll just punch in the log on that, 4.94 plus 1.4, 9.06. So that's the pH of this buffer based on that that solution mix that we had wherever we had it back up at the beginning of this thing. And so if you study this, it's really nothing more than what I did in applying it to the ice table. Now all the ice table does is gives you reference to the common ion effect. So you put in your initial with your common ion and then change an X to the equilibrium and substitute in the equilibrium expression. Solve for the unknown. In this case, it just happened to be the hydroxide. Or if this is your hydroxide, you can get your hydronium, Kw, over the OH like this. And 10 to the minus 14 over 1.15 times 10 to the minus 5 molar, and 8.7 10 to the minus 10, and then get your pH to equal minus log of that number, which will give you the 9.06 also. So this or that approaches to getting to the appropriate answers in this, if it's what you're trying to do. I know it's a lot of scribble in a hurry, and I don't know any other way to do it.